Hello and welcome back to Leet Logics. This is the count vowels permutation. It is a LeetCode hard, but I guarantee you it will not be a hard question for you if you watch the video till this end. So the number for this is 1220. So in this question we are given with an integer and our task is to calculate how many strings can be performed under the following rules. So we are given some rules such as the each character is in lowercase. So this is the first rule. Each character will be in the lowercase, we know. Then we have each vowel A may be only followed by E. So A will be followed by E. So if there is A, the next will be always E. And if each vowel is E, it may be followed by A and I. So if vowel is E, the next may be A or next may be I. Or if each vowel is I is followed by another I. For I it is given that I may not be followed by another I. So if it is I, it can be any element, any character other than I. Then for vowel O, we can have I or U, or and then for vowel U, we may have an A. So what we can do is that we can create a function which takes the index and the last vowel used, and then what we can do is that we can perform all the steps. So for writing a recursive function we need the following. So first of all I will tell you the approach how we are moving. So in a given uh, value for n, we'll move from n to 0, that is top down. So in this case what will be our base case? So our base case is that when our length becomes 0, and when length becomes 0 there will be only one possibility, so we'll return 1. Otherwise we'll keep a count and we'll perform all the operations. We'll perform all the operations on the following, like if we'll check what are the possible integers which can be there. So we'll perform all the operations and then we'll simply return count. So for this we need to represent the vowels in terms of integers. So we'll take 0 as no integer, no character, 1 as A, 2 as E, 3 as E, 4 as O, 5 as U. So let me show you the recursive code. So you can see I have defined a function find permutation which takes integer, two integer actually. So the first one is actually the index and the second one is actually the last vowel used. So we are calling the find permutation for n and 0. It is 0 because we haven't used any of the following vowels till now. So first of all we write the base case. So base case is when length actually becomes 0. So when length becomes 0 we will simply return 1. Otherwise we'll keep a count. Then we have to perform all operations. All operations we need to perform. So let's check. If count equal to 0. So what was 2? So 2 was E. So if there was E, may be followed by only A and I. So we are calling it for 2. Okay. We are keeping the count, calling it for 2. No, actually sorry. Then if it was E, it may be an I, so we are calling it for 1. Otherwise, if it was 1 and 3, this one, A and I, we are calling it 2 for 2. Then if we last wasn't 0 and last wasn't 3, then we are calling it for 3. Okay. This is actually for it may be not followed by another I. And then we have 3 and a 5. So 3 and a 5 will be followed by O. O was actually 4 here, so we have given 4. And lastly, if it was uh, 1, we are simply returning with 5. We are actually calling the recurrent stack with 5. Then we have last equal to 0. So if last was equal to 0, then we need to check all the possible characters which we can keep. So then we run a for loop from 1 to 5 and we find all the possibilities keeping each character as the first element. So this loop, what it does, it calculates all the possible values, all the possible permutations and return the count. So this solution actually gave a TLE, but it was very important for us to understand how the recursion works for this question. So let's go through the code one again. First of all, create a function find permutation with integer and integer to store the index and the last used. Then we have to write the function. First of all, we write the base case. Base case is when length becomes 0 because we are moving from n equal to n to n equal to 0. So when n length equal to 0, we returns 1. Otherwise, we keep a count, we perform all operations. And how we are performing the operations? Like if it is followed by e, so last equal to 2. If last equal to 2, we'll call for 1 because we are moving from the last. So we'll check from the last. Like if e occurs, then the next element, previous element should be always a. So we do this. Similarly, we do perform for all the operations here. Like if the last used is a or last used is I, we call it for e. Or if the last use is not I or the last use is not 3 we are taking for O, so we call it for 3 actually. So similarly we have done for all the operations here. This one is special because when first time we are calling with a 0. So for 0 there has been no character used, so we'll call for every possible character at the end. So that's why this is also possible. And then we'll simply return the count by mod. So this was my recursive approach. This will definitely give a TLE because the time complexity is some 6 to the power of n. So we'll now have to memorize this. So to memorize this, I can show you. This was our recursion code. The next to it is our memorized code. So we have used memorization array, you can say 2D array we have used to memorize it, filled it with -1 as usual, as we do it in memorization, and then we have simply passed the DP along with the function. And in function we simply add here nothing, but if memo of length and last is not equal to 0, we'll return memo. Otherwise at the end what we'll do, we'll return simply memo and last equal to, return memo and last, len and last equal to count modulus mod. So otherwise we have to make simply no change. And you can see this solution, this solution was actually accepted because uh, uh, it has removed overlapping subproblems. In the uh, recursive approach, there was overlapping subproblems, and the time complexity for that was actually 6 raised to the power 5 into n. So 6 to the power 5n is actually a big number, and the space complexity for the recursive one was also of n. So that's why it was actually not an efficient approach. But in this approach, we have actually tried to remove all the overlapping subproblems by calculating it in advance. So we have calculated the overlapping subproblems in advance, and no problem is checked 2 times, so this is solved in a faster manner. The time complexity for this will be actually more than the previous solution, but the time complexity will be less than the recursive one because we have used memorization DP. So this was my uh, memorization solution. Now let's come to the tabulation approach. So you can see this is my memorization approach. If you want to take a screenshot, please go ahead. You can take a screenshot. Okay, now let's move to the tabulation approach. So tabulation approach is another dynamic programming approach where we fill 2D array iteratively. We consider all the cases in this also, but we start from bottom up. We do a bottom up traversal. In the last approach, we were doing a top down. That means we were moving from the top to downwards. We were expanding in it, but now since we are doing bottom up, we'll take all possibilities, we'll sum up and we'll move up. So that's why the approach is also called a bottom up approach. Now let's see the top down bottom up approach as well. So the bottom up approach will be a bit similar to what the recursive approach will be, but it will be in the like zero, it will be 1 to n rather than n to 1. So first of all, we'll take the mod, then we define a long DP. We fill the first row. We fill the first row with actually 1, because uh, the DP which we are creating is in the form of n and last. Like if you know, the DP will be the first. The DP of I will store the length and DP of j will store the last. So whenever length equal to 0, we have to always return 1. So that's why we are filling the first row as 1, because whenever the length will be 0, we have to return 1. So that's why we are filling the entire first row with 1. Otherwise what we are doing, we do a traversal of the entire DP array. We move the length to all the possible values, that is 1 to n, and we move all the possible last values, that is 0 to 5, and then we keep a count. And in this, what we do, we simply do the same logic as we have done in the recursion, and just replace the recursive function with the DP. Like you can see, here is the recursive function and here is the DP. So if last equal to do, count equal to count plus find permutation len minus 1 and 1. And what we are doing? Count equal to count plus DP of len minus 1 and 1. So simply return this part with a DP and your tabulation is done. You can see this is the tabulation approach. Here we are moving from 1 to n. There we were moving from len minus 1, len to 0. So this is the top down, this is the bottom up. So this is a tabulation approach, and at the end simply we have to return n of 0, dp of n and 0, because the dp of first element will actually store the dp of the last row, and the first element will actually store our final answer. Now in this question you can see that we always need a dp of length minus 1 and 1, but we are why are we storing a 2D DP for this? We can only need the last row which was used or created, and we can do it, so we can space optimize it. Instead of using a 2D DP, we can simply use a 1D DP and store the last previous row. Actually, we can actually store the previous row and use it here, because we are only using the previous row here and no more other rows. So we can definitely space optimize. By the way, if you want to take a screenshot of the tabulation approach, please go ahead. You can take the screenshot. Then we'll move to the space optimized approach. So in the space optimized approach, we'll take two different arrays. One is the last used and one is the current. So the last will be used to store the last rows, and the current will be used to store the rows which we are generating. And at the end we'll do what? Last equal to current. So the current will be stored into the last. Otherwise it is same as the tabulation approach. Like you can see, this is the tabulation approach. Simply where the DP was 2D, we define a 1D and another 1D for storing the current row. And at the end we have to do a DP of last equal to current. And I'll tell you one thing. Wherever this was written, DP of len minus 1, you have to replace it with DP last. Okay, and wherever DP of length was written, you have to replace it with DP of current. So you can see wherever length minus 1 was written, it is replaced by DP last, and the J becomes the first index for you. And similarly, DP of length becomes DP of last. And only this operation is actually extra for us, storing the current into the last. And here also you can see, here we store, instead of n, we store the DP of last. Now you will ask, why do we have used the last if you have said like we have to use the current for DP of n? It is because we have to, in the last iteration we would have swapped the current into the last. So our answer would be actually in the last, and our current scope ends here. That's why we have used the DP of last here. So this was my tabulation with space optimized approach. If you want to take a screenshot, please go ahead. Oh, and this gives excellent runtime as well for me. And the space complexity for this is actually O of 6, that is constant. So this is a highly efficient approach. You can use the following, you can use all these approach in an interview too. And if you, I guarantee you, if you solve this question in an interview, in front of an interviewer, from recursion to tabulation, don't do the space optimization approach. I guarantee you, you will be selected for that interview. So this was it for today's video. Please do like the video, subscribe to the channel, share it with your friends. I hope you like the video. Thank you for watching. Have a nice day.